Next, the talk by Professor Mei Huang. Mei, could you share your screen? Yes. Yes, okay, so please go ahead. Yeah, Mei will talk about the Chiral dynamics and the gluodynamics and the rotation. Please. Mei, are you here?
Okay. Yeah, okay, sorry. I was okay. So, okay, thanks the organizers. And so we meet here. And so I will the chirodynamics and the glue dynamics and the rotation. So I will firstly will give a very brief introduction because Kenji introduced a lot about the physics and the rotation. And I will talk about the chirodynamics and the rotation in the framework of engineer model, and then investigate the glue dynamics and the rotation in the framework of holography, and then give a summary.
Sorry, can you full screen your slide?
Oh, full
Can you
screen.
make
Okay.
full screen of your slide?
Yeah. Okay. So it's okay now. It's okay.
Oh, yes. Thank you. Yes, yes.
Okay. So I think this QCD matter and strong magnetic field and also very fast rotation already attract a lot of interest. And this for non-central heavy ion collisions, this angular momentum can reach 10 to 4th, 10 to 5th h bar. And this recently the experiment also observed the spin polarization for some vector mesons. So okay, first part I will consider the chirodynamics and the rotation. So for this part, so we use engineer model. So we follow the notations in this paper by Jin Feng and Jiang Yin. And so we take the two flavor engineer model, and the angular velocity is taken into account by this spin connecting. And so this is equivalent to take into account this omega j shift of this omega j. So with this, so we can investigate the chiral phase transition. For example, this constant quark mass or the chiral condensate as a function of omega for different mu. So we see that actually there are two different first order phase transitions. So one is for this one is the first order phase transition at 0 mu and or small chemical potentials, and another first phase transitions will happen at high chemical potentials. Okay, so this gives actually this three-dimensional phase diagram for this T, omega, and the mu. So you see that at these two corners, so one is in the high omega region, and another corner is actually in the high mu region. So you can see that two corners, there will be first order phase transitions. And also we consider, we investigate the scalar mesons and also vector mesons as a function of this angular velocity. Okay, sorry, I must point here actually, this omega, this angular velocity from this Lagrangian, you can see this omega actually plays a very similar role as this chemical potential. So this also pointed by Kenji. And indeed, actually, for scalar mesons, you see that this scalar and pseudo-scalar mesons as a function of angular velocity, actually, you see that it's very similar to this scalar and pseudo-scalar mesons as a function of chemical potential. You see that so very much similar. Okay. And recently, we also investigated the vector meson as a function of angular velocity. And so we just calculate this RPA for the vector mesons. And we decompose this spin component for rho mesons. And very explicitly, I will say that this Zeeman splitting effect for different spin component of the rho mesons. So, and we see that for this spin component SZ1 equal to 1, this spin component vector mesons decrease linearly to 0. Okay. So actually, okay, I move here. Okay. And it goes to 0. So this is very similar to the effect of magnetic field on the charged rho meson. Of course, Maxim Chernobyl, he proposed this charged rho condensation in with under magnetic field. But here, because this happens, I mean, this component decreases to 0 at a very high omega, so we cannot really say that this will be this spin component vector meson. So this behavior itself is very interesting. And yeah, basically, so I just want to point out that the rotation effect on scalar mesons is very similar to the chemical potential, but the effect of rotation on vector mesons is actually very similar to the magnetic field on the charged vector mesons. And also for thermodynamical properties, so we also investigated this in the framework engineer model, and we see that with the increase of angular velocity, so we can see the enhancement of the thermodynamical properties. For example, pressure density and energy density and so on. Okay, so as I showed that actually the rotation plays very well. Basically, the spin 1 particles or vector particles are very sensitive to the rotation, and the gluons are actually spin 1 particles. So we should, in some way, we should take into account the effect of rotation on gluons. But for four-dimensional, we don't have a very good four-dimensional effective theory to deal with gluons. So in this part, I will use the dynamic holographic QCD model. So I will introduce briefly this holographic duality. So this is actually based on this ADS-FT duality, but based on this, we expect that there will be a general holographic duality between any d-dimensional quantum field theory and the d+1 gravity. So in this case, we can build up a kind of holographic QCD model, which is very similar to this renormalization group. So this is actually, we put spins on lattice, and when the lattice size changes, so the system actually shifts from UV to IR, and the coupling constant also changes. So this is basically the renormalization group. So based on this, so we can promote this coupling constant to a dynamical field, for example, this Denton field. And then we construct such kind of a dynamic holographic QCD model, and by introducing this Denton field to describe gluon dynamics, and also introduce another scanner to describe the chiral dynamics. So then by solving this system dynamically, we can get the deformed ADS5 matrix. So this is actually, we can self-consistently solve the deformation by the IR dynamics. So this is our framework. Okay, so we firstly construct this GNOME dynamics. This is GNOME background and described by the Stinnerton field phi. And with this, then we add these hadrons or matter fields, including scanners and vectors, on the background of this canonic background. So our total or full dynamics is basically the GNOME dynamics plus matter part. So then we can investigate many physics in this framework. And this framework is actually, okay, so this is our framework. This is called a dynamic holographic QCD model. So we have this GNOME dynamics described by this Stinnerton background, and the quark dynamics or matter dynamics described by this flavor background. So this is very similar to this top-down model described by D4, D8, or D3, D7 system. And also it's very similar to this PNGR model, this polygraph loop potential NGR model. So this flavor background is very similar to, well, actually it's the same as the second model, basically.
Знаете, я сейчас нахожусь вне экологии в течение достаточно длительного времени.
Okay. So this is so this Stinnerton background actually plays the same role as this polygraph loop potential. So okay, we can. Oh, okay. This is the details of the D4, D7, D4, D8 brain, and this is the details of the PNGR model. So I skip these two slides, and we can. I just show that from this dynamic holographic QCD model, so we can get this chiral phase transition. Well, this is a chiral phase transition, and this is a deconfinement phase transition 9. And this result is very similar to the result from PNGR model. So this is given by Sasaki and Radnish and so on in 2006. So we can get this separation of the chiral phase transition and the deconfinement phase transition. This, we can call this chiral symmetric but the confined phase here. Okay, with this, so well, we can extend this dynamic holographic QCD model to a more general Einstein-Maxwell Stinnerton system, and because this geometry Stinnerton field, you can input one. For example, in our previous model, so we input Stinnerton field, but you can also input the metric, the deformation of the metric, and then solve out the Stinnerton field. So, but the system basically is the same. So here we took another Einstein EMD system. So we gave this deformation of the metric structure, and this is actually we took from this Bayesian group, and then so we can fit the parameters of the system by using lattice results at zero chemical potential. So we use lattice result for pure GNOME system, this blue dotted line, and also for two flavor system with this green band. So by fit the thermodynamical potentials, so then we can fit all the parameters, these parameters. So then basically we use this two systems to investigate the rotation effect. So well, we extend this model EMD system to rotation. So this omega is a dimensionless angular velocity parameter. So this is ranging from 0 to 1. Okay, this is the setup of the model. And then, so we investigate, for example, the thermodynamical potentials, thermodynamic properties, and the rotation. And for pure gluon system as well as two flavor system. So we can see that we can also get the enhancement of thermodynamical properties with this angular velocity. And we can also investigate this deconfined phase transition and rotation. So for pure gluon system, so this phase transition actually is the first order phase transition at small mu, but well, at the first order phase transition at a small mu and crossover at high mu. So we can see that this is phase transition 9 as a function of omega with different mu, and this is phase transition 9 as a function of chemical potential for different omega. So we can see this, for example, this with the increase of omega, so the CEP point, this critical point, shifted to the left part of the phase diagram. And for two flavor, this is still for deconfined phase transition 9. But these are crossovers. So basically, so we can see that with the increase of angular velocity, so this phase transition 9 shifted to the lower part of the phase diagram. And we can also investigate the heavy quark potential and special Wilson loop and Polyakov loop and the rotation. And this is a heavy quark potential. And you see this with the increase of angular velocity. So this screening part actually decreases with omega. And the special part of the Wilson loop increases with the angular velocity. So this angular velocity, this special Wilson loop describes actually the this linear confinement for the special Wilson loop. So this is a special confinement. And also we can check the Polyakov loop for pure gluon system and two flavors. So you see that actually you can see this first order phase transition, this TC with different omega, and this is corresponding to the TC determined by thermodynamical potentials. So this is a kind of self-consistent checking. Okay. So I think I'm finishing very quick. So the summary is that so we investigated the effect of rotation on chiral dynamics in the engineer model, and we investigated also the rotation on gluodynamics in the holographic QCD model. And we see that the rotation plays the similar role as the chemical potential on thermodynamical properties and also for scalar mesons. But the rotation affects the vector mesons sensitively, and actually for vector mesons, this rotation plays a role like a magnetic field. And we also see this QCD phase structure changes and the rotation, both for chiral phase transition and also for deconfinement phase transitions. For the outlook, actually, we are also now investigating the inhomogeneous structure in the holographic QCD framework. And we are also investigating the vortex structure. And for the how to connect the meson spectra of these vector mesons. So with the spin polarization observables, so we are now still, well, we think about that, but we didn't find the way how to connect this part. So we are still working on that. Okay, so I think I'm finishing very quickly. Okay, thank you.
Okay, thank you, Mei, for the very good talk, and also thank you for saving some time for us for discussion. Maxim, can you ask your question?
Yeah, I would like to ask one question, just a comment. As Kenji told last talk, and we know that the boundary are very important, and also size of the system is very important. And for your large frequencies, which corresponds to approximately 1 GeV at most, the size of the system should be approximately 0.2 Fermi, which is very close to the confinement regime. So you show your dependence on your potentials, and your potentials becoming flattened at some specific distance. And I'm afraid that they correspond to just to speed of light cone. Have you checked this? Or
Yes,
speed of light slope?
Yeah, I think actually this is a very nice point. Yeah, we can check this. And actually for the outlook, I mean, for this vortex structure, actually, we are also taking into account the finite size effect.
Okay.
Yeah, but I didn't have the result yet. Yes, you wrote to me some days ago, but yeah, we yes.
Because just a very short comment, because in Kenji's talk, he specifically have shown this part from Vilenkin's paper. And in fact, if you don't respect boundary condition, then population indices, the populations of bosons can become negative, which is unphysical. And it can give contributions if you don't respect this quantization at the finite boundary. That's extremely important comment.
Oh, yes, we got a negative sound velocity, indeed.
Yeah, okay, yeah. Okay, good. Thank you very much.
Yeah. Okay, thank you very much. Yeah.
I would have also a question regarding the astrophysical consequences. For example, when you look at a neutron star merger, after the two neutron stars merge inside the hypermassive neutron star is strongly differentially rotating, and when in the interior then the hadron quark phase transition comes, what possible astrophysical consequences could that have?
Yeah, this actually would be very nice if we can have such kind of effect. So we actually considered tried to consider rotation effect on neutron stars. But for neutron star, I mean for stable neutron stars, I think the rotation is very small. So
yes, exactly. I'm more focusing on the post-merger phase of neutron star merger remnant, and there we would have a strong differentially rotating object.
Yeah, that would be very, very interesting. Yes, yeah, we can consider that. But I think for equation of state, maybe not too much, because as you say that the equation of state, the thermodynamical potentials are not affected too much. Yeah, but I think we can try that. We can try to look at that.
Okay,
but I don't know how, yeah, but I don't know whether this vector meson would affect would have some results or some phenomenological results from neutron
so for example, when you look at the fluid cells, they could undergo a phase transition to going into the deconfined phase and out within 1 millisecond roughly, yeah, when the freezing out then again occurs, yeah, then there could be some including magnetic fields, some yeah, consequences. I don't know.
Yeah, I think it's good. I mean, we can have some look on that direction. Thanks a lot, Matthias.
Okay, thank you.
Okay.
Okay, so I also see a question in the chat from Dennis. So Dennis, would you like to ask the question by yourself?
The first question, maybe the splitting, like in the Zeeman effect, can be explained in terms of gravity-magnetism. Actually, so rotation is equivalent to gravity-magnetic field. So I think it's quite expectable.
Mm-hmm. Actually, I kind of lost my screen. Okay, so moment. So, okay, I can check the question. Okay, I lost my screen. So.
Yeah, that's the comment. Yeah, the comment is that the rotation
Okay.
is similar to the gravito-magnetic field. So the splitting is.
And about the model concerned, maybe it's too broad question, but why actually Einstein-Maxwell-Dilaton model you found out to be the most appropriate one? For example, not slow wall model, soft wall by Sonstick.
Oh, okay. Actually, software model is like okay. This is actually the software model part. So for software model part or hardware model part, actually this is they only take into account this matter field and in the background of the ADS5. So this is basically this action. This is the matter field. So this is basically the software model or hardware model. But in our framework, basically we coupled the matter field with the gluodynamics. So this is like, well, if I comment like, so software model is like a second model and actually like this NGR part. And this background, the gluodynamics background, this is actually plays a role as this polyactive loop potential part. So I think this is the difference.
Okay, thanks.
Mm-hmm.
Okay, so next question is from Nugaza. Please ask your question.
We have seen that we have the addition to the string tension in the linearly rising potential, right?
Yeah, this Wilson loop, this special Wilson loop, you mean this part or?
And then even if we have small negative value of the original tension, which corresponds to the Debye screening, by this correction, we can change sign. So it corresponds to the phase transition from the screening to the confinement phase. Okay, that's all.
Okay. But I have no idea about that. Yeah, okay. So, but yeah, this is for screening. This is for the basically this how do you say? This zero part of this Wilson loop, and this is for the special part of the Wilson loop. So they are different physics. So one is for the electric part, and one is for the magnetic part. I think when we talk about the deconfined phase transition, we are talking about this polyactive loop part, basically the zero component of the Wilson loop.
Okay, good. If you, okay, I don't see further questions, so let's stop here. Thank you very much, Mei, for the nice talk.